All right. So when it comes to AC, right, one of the commonest waveform that we've seen is the what you call the sinusoidal curve, which is what we have here, right? The very commonest one. But then one problem is that we don't have to always be drawing it like this, and for a particular circuit, especially in AC, it could be that there are slight changes between the voltage and then the current, right? Because we said V is equal to IR, right? These ones are the ones that change, like they are kind of like have waveforms in they are the sinusoidal quantities, right? They change with time. Okay. So it's not always that we can draw them, drawing the curve always, right? And then we said there are times where one will start before the other. So we look at it. So in order to make it simpler, we do what we call phases, right? So what we are doing with the phases is that whenever we have a particular sinusoidal quantity, we can use the phases to represent them. And then when you look at this line, so this here is the phasor that we are talking about, right? So basically the length of this phasor here is what determines, so let's say the length of the line, right, is what determines the RMS value of it, whether it's voltage or current, right? So the length of the line is what determines the RMS value of that sinusoidal quantity, right? And then the direction tells us something. So now let's look at this. So when we look at this particular sine waveform that we have here, this one, you can see clearly that they are supposed to be on the same line. You can see clearly that the voltage and the current, the voltage, the purple, the current, the yellow, right, actually together, right? Because it's down manual, so that's why we are a bit apart. And for clarity, that's why we bring them a bit apart. So on this particular graph here, they are together. So that's why we say they are in phase. So when we are drawing their phase diagrams, is that they are together, right? And then when they start on this particular line here, which is the x-axis, the x-axis could be time, right? And we said something about if you have a sinusoidal quantity, is let's say the peak value, right? The peak value or the maximum, right? And then you have sine, and then we have WT here, right? Which you said this side, this WT here, right? Which you said this W is the same as 2 pi f, right? So if we haven't time here, meaning that if you haven't time here, it's either we write this one here in time or you write it in theta, right? Yeah, where the theta is the WT. The theta is the WT, which is also a function of time, right? So if you don't see time and see theta, it's the same thing. So you see for this graph here, when they started from the origin, right? They started straight from the origin, which is the 0, 0, and they moved, right? So when a particular waveform start like that, so we see that when it starts like that, you see what it shows is that it starts from the very 0. So let's go back to coordinate system. For coordinate system, we have something like this and like this, right? And then this is like the positive x, negative x, so x, x, and there's positive y, and there's what, negative y. And then when it comes to rotation, we use this as our reference, right? So we start from here and then we move this way, right? So there's the reference, the starting point. So what it says is that since these two quantities, sinusoidal quantities on the original waveform are starting just at the origin, right? So if they are starting just at the origin, we use this reference here. So we say they are on this very line here, right? So when you are drawing their faces, they are actually parallel to the x-axis, right? So that's why I write them this way. And then one thing that happens is that since these two waveforms for the voltage and the current are started from the 0 and they add together, so when we are drawing their phases, we draw them together like this. So and then we said that the length is what determines the RMS value, right? Okay. So what happens? What if it happens that the what do you call it? The current and the voltage are not in line. In this case, we've seen a new term. So let's write it out. So it's either they are in phase or they are out of phase. These are the terms that we use to describe these things. So we said the in phase is when, whether they start at the origin or they don't start at the origin. So when you're talking about waveforms being in phase or not, you can't talk about just one. You can talk about two waveforms, three waveforms, or whatever. But the main thing is that when we say they are in phase, what we are trying to say is that they start together. Let's see. They kind of like start together and they reach their peaks together. right? So it could even be that their peaks are not the same, but let's say there could be another curve here, but then they peak together. They get to their peaks together, right? They get to their peaks together at the same time. So if you trace the time, this is the peak for this one here. This is a peak for this. So let's say peak 1. This one's peak 2, right? So if you trace the time, see that they all peak at the same time, right? Yeah. So that's when we say they are in phase. But if it happens that they are in this way, right? You can see that for this particular one here, let's see. It's valid. So when you look at this particular one here, they get to their peaks not at the same time, right? So let's see. So for the voltage, the peak is about here, right? So when you trace it, the peak occurs about, let's say, 3, right? But for the current, the peak occurs about 4. So that's why we see they are out of phase, right? And when you look at it very well, you can actually see that they don't start at the same time, right? So one starts before the other, and as a result, one gets to its peak before the other. So that's what we mean by when they are out of phase. And as we started, we were saying, when it comes to representing these sine waves, we don't want to always draw the graph, so we use the phases, right? And because these two are out of phase, their phases won't be in line, right? So there'll be a phase shift. So that's what we see. So let's see. So we introduce another term, which is a phase shift. Because one gets to its peak before the other, we see something that's a phase shift, right? So one has shifted away from the other, unlike the one we saw previously. And because there's a phase shift, we have what we see a phase angle, right? With the angle to represent them, because we said how we represent a sinusoidal quantity, right, is we have the peak, right, and we have the sine, and we have the WT, right? And then this can be written as 2 pi f and then t, right? But we said that this WT here is the same as this theta, as we've seen here. So let's see. So it's the same as saying Vm, right, sine theta, right? And we said this sine theta is the same as Wt. So Vm sine Wt, right? So if you don't see time and you see this, so that's why we see this. If they don't, so when we start here, we said they don't occur at the same time, right? Because at times we use what they call the theta, we say there's a phase angle, right? Or there's a phase shift, right? So it's not always that you can see this in time, it could be in theta. So there's a phase shift, right? Or there's a phase difference, right? So a phase difference, a phase shift, these are all terms that represent the same thing. So a phase difference. The same as a phase shift. Yeah. So these two are the same. Phase shift, phase difference, and as a result, we have what we see a phase angle, right? Okay. So when you look at this one very well, let's go over this. When we look at these very well, we could clearly see that which of them starts first. The waveform for the voltage starts first, right? Just by the way, these phase shift don't occur on their own. There are certain elements that when introduced in the circuit, they cause this phase shift. At times, we want them to create certain effects. So something like an inductor, a capacitor. These are the things, some of the things that introduce a phase shift or a phase difference within for the sinusoidal quantities, right? So we are going back. So let's look at this. When we look at this graph again, one thing that we can see clearly is that one starts before the other, as we said, right? So there's a phase what? A phase difference or a phase shift, and as a result, there's a phase angle, right? Okay. Which of them starts first before the other? Which of them gets to its peak before the other? It's clear that the violet line, sorry, the purple line, right? This one right here. It is very clear that a minute. It's very clear that this one, the voltage, which is the purple line here, is the one that gets to its peak first, right? So somehow, because that's the one that gets to its peak first, or the one that starts first, we say it's leading, right? So you see that this one starts, or it gets to its peak first. You could see that that particular one gets to its peak first, right? Before this one does. So we get to say that the voltage here, so because there's a phase shift, a phase difference, right? There's an angle of phase angle, right? So another thing that we see is that because the voltage curve here, waveform here starts and gets to its peak before the yellow line here, the yellow waveform gets to its peak, we get to see that what the voltage or the V leads the I, right? So basically the voltage, right, leads the, what do you call it, the current, right? So if we're to happen to be, so this same one can be said another way. So there are two terms that we use. The other word is lag, right? So we can see that the current lags the voltage, right? So these two things here mean the same. So it's either you use lead and you just say which one is leading, right? Or use the other word and reverse it, right? So lag. So it's either lagging or leading, right? And because there's a phase shift, right, or there's a phase difference, the what do you call it? The phase angle are usually measured in degrees, right? But here, because everything is in time, we can't use this one as an example, right? But we are going to look at a very clear example. So a minute. So now we've seen the terms. You can see that the voltage comes first, all right? The voltage leads the current. So this same waveform here, this same graph here, can be described in the same way and say that, and we could see that what the voltage leading the current. So we can see that the voltage leading the current is the same as the current lagging the voltage, by right? Okay, now let's move on. So it's clear very here that because the voltage here starts from the very, what do you call it, the very origin of the graph, the voltage will be like this, right? Right. So as we said, x, y, z. So this we have x here positive, x here negative. So x positive, x minute. No. So this is positive x, this one negative x, this negative y, positive y, right? We said this is our reference, right? The positive x-axis is our reference, and because this very one here, the voltage starts at the very origin, is in line with the x-axis, right? So there's no difference with this starting point and that of the y-axis, sorry, the x-axis, positive axis. So that's why for the voltage it's straight like this, right? It's in line with the x-axis, right? But then there's a phase difference, right, between the that of the waveform of the voltage and the current, right? So which one is leading? So we said that for this particular waveform graph that we're having here, the voltage is the one leading. So if it's the one leading, mean that if the voltage is about here, right? We said that, a minute, let's go over this one more. From this waveform here, the graph, you see that the voltage what leads the current, right? And if it's leading the current, another way to say is that the current lags the voltage, right? And we said that if we are doing from the xy axis, we read this way, as we've seen here, read this way, right? This way is positive, right? But then we said that this same thing represented lag, right? So if the current is lagging, and then we said the voltage is in line with the x-axis, it's the voltage. So the voltage is this, is in line with the x-axis, right? So one way to write it is that the current lags the voltage, right? So we just bring the current. So instead of going in this direction, the current will be somewhere here. So to have to move to catch up with the voltage. So that's why the current is this way, right? So the current lags the voltage, right? So this one is that the one actually represents this graph here. If it were to happen that we have the current rather being starting here, right, and then the voltage started here, then the best way to represent will be this. But for this particular one here, how we are seeing it in this graph here, the one that represents it best is this waveform here, right? And then one thing to note is that for every circuit, because what we'll be doing so far is that we've said so far is that we have V is equal to I. So the Ohm's law is what is describing all that we've been doing so far. V is equal to IR, right? And then we said the quantities that change with time, especially in AC, V and then I, right? So meaning that whatever circuit that you have, whenever there's a there's a phase shift or a phase difference, right? There's a way to use just the phases, which we've done today, to represent it. So now we are going to look at an example. So let's see. Okay, this is what we have. It says the voltage source in the particular circuit, in this case, has an RMS of this, so right, has an RMS of 240, right, volt. That's the voltage source and the frequency of this. And then, though this is not said, the moment you are talking about a voltage source or current source or whatever, let me write this again. You said V is equal to what? IR, right? And the quantities that in AC that change with time is V and then I, right? Okay. And then whenever any of these source, whether a voltage source or a current source, has a frequency, meaning that it's actually an AC. So at times it won't be said, but you have to understand that, meaning that it will be AC, right? So a voltage source has a VRMS, or what do you call it? A root mean square value of 240 volts, right? And then the frequency of this, right? And that very voltage source delivers a current of 10 amperes, delivers a current of 10 amperes. Yeah, something's missing, but this one's actually delivers a 10 amperes RMS, so it's actually RMS current to a circuit, and it says that the current lags the voltage by 30. And I mean here our one thing the first thing we have to do is that we have to draw a phase diagram for the circuit. So as we're saying, we've been given the voltage RMS of the circuit, what do you call it, the current RMS of the circuit. Now we are supposed to use just phasors to represent them. Instead of writing the whole wave something, we can just use phasors to represent them, right? So what did we say? It has given us the voltage RMS, and then we said to try it, you can pause and try, or else you can follow up, right? So we're saying that the voltage RMS is 240, right? Here we are not drawing to scale, so we are just going to draw anything, but somehow to show a difference, right? So we are saying that the voltage source is actually the whole thing, and it's given the VRMS of this, right? Okay, so now that's what we do. If we use that one as the reference, right, we can put it about here, right? And I'll give it a direction. This freehand, so pardon if it's not parallel to the x-axis, right? And then it says for 240, right? So 240 volts. So that's the only thing we know about the voltage, right? Okay. When it comes to phasors, you don't use the frequency to actually draw the phasors, right? Okay. And then it says delivers a 10 amperes RMS current, right, to the circuit. And then now the current lags the voltage by 30, right? And it says draw a phasor diagram for the circuit. Okay. All right. So now we've drawn the voltage. The next thing is to draw the current. We know the current lags the voltage by 30 degrees, but then the voltage is what, about 10, just 10 amperes. So in terms of value, this is 240. Because we're not drawing to scale, the current should be shorter in terms of the line, right? The length of the line. So the current can be something like this. So compared to 240 is too much. Can be about this, right? So there's the current, the RMS current, that's what, 10 amperes, right? And we said the phase difference is what, 30, right? So 30 degrees. So that's it. So the whole circuit has been represented using this, right? The quantities that are changing with time, that's the voltage and the current, have been represented using these phasors. And that's it. But then again, this is not what drawn to scale. Let me write it here. Not drawn to scale. If it to be drawn to scale, there's a way to show that there should be a way that 240 number, right, to have a particular length of line, 10 will have a particular length of line, right? Yeah. So this is not drawn to scale, right? But then we should show that somehow the 240 line, right, phasor line is longer than that of the 10 amperes, right? So yeah. So now we've represented the whole circuit using phasors. So the next thing we want us to do is to write the voltage and the current as a function of time, right? Okay, this we've been doing this a lot, right? So what we've said is that if you want to write sinusoidal quantities, let's say voltage, right? If you're writing the sinusoidal as a small v, right? This is the general formula, and then we have the peak value here. See, yeah, the peak, so maximum, right? And then because they are sine waves, this one hasn't been specified, but then we said that when we are doing phasors, our aim for these phases that we are doing here are just sine waves, right? Okay. So sine, and then we said it's either WT, right? Or we have Vm, and then we have sine, right? And then we have 2 pi ft, and we put a dot here. Okay. Or we have it to be Vm, right? Sine, right? And then we have what? Theta. These are the three ways, the basic theories of representing the voltage. AC, right? The current is the same way. So we have V, sorry, not V, should be I peak. A minute. So did understand so far? Just trying to write out the basic ones that we've done, right? But if you've not done this, you can go back and check the discussion that we had so far. Right? So we are just writing out the basic representations of these quantities. Then we will go back and try, and then using the information given in the the problem given, we try and write it out. So sinusoidal I, so we have I max, right? This current, and we have sine because they are sine waves. See that W, sorry, yeah, it looks like W, but that's the angular frequency, right? Or I max sine, we have 2 pi f and t, right? That's a period, or which is the same as I max, and we have sine just theta, right? So now when you have this in mind, you look at the question. What did the question give you? The question gave you frequency, right? So which of these forms has frequency in it? So you see this one doesn't have frequency, this one doesn't. So the appropriate one to use in this case represent the 10 is this, and the same thing will happen for the voltage, right? It will be this one here because they've said something about frequency, right? This one here is RMS, right? You have RMS, you have frequency, but then the frequency is given, so the one that is very appropriate to use will be these ones, right? Okay, so let's see, we're representing the voltage first. So now let's see if we have everything we need, right? Okay, so if we are using this one, we have the, what's the name, we have the frequency 2 pi is constant, and then the t, which is the period, right, will be constant, right? Okay, but we've not been given that one, so we have f, right? T 2 pi will not change, so we have this, right? The only thing we don't have is the VMX, and because you have sine waves, there's a way to write that out. There's a way to find the the peak value. So let's do this. What did we say? We said for sine waves, when we're trying to find the, let's say, VRMS, is the same as when you take the peak and divide by square root of 2, right? So if you are trying to find the peak, when we be given the RMS, just means that the peak, right, will be root 2 times the VRMS. So now we have everything we need. So the peak for this particular quantity here will be root 2, right, times the VRMS, which we've been given for the VRMS to be 240 volts, right? 240 volts. Okay, so let's see. 240 volts. All right. That's root 2 times 240, right? So 240 times what? Root 2. And that gives us 339.411 about 3 volts, right? Yeah. So the same thing will happen for the current, right? The same thing will happen for the current. So for the current, let's look at it again. We are using this representation here, right? So we have the T. T has not been given, so it will just be there, right? The period has not been given. It's a function of time. So whatever the time it is, then the actual quantity will change, right? Let's see. Let's represent the voltage first. Now we found what we need for the voltage, but let's find it, right? So let's see. Now to find the voltage as a function of time, the V here will be what? So we have the Vm, that will be 3. It could be, just write this 39.4113, which is the peak, and we write the sine, right? And then we have 2 pi. F is 50, right? So that will be 100, right? So we have 2 pi F, and then T. We have 2 pi here. This F here was what? 50, right? Where is it? This is it, 50 hertz, right? So 50. When you multiply this 50 by the 2, that gives us 100, right? So sine 100, right? And we have what? So this is out, so sine 100, and we have pi t. If you want, you can even turn the pi to a value. But this same thing, you could avoid this one here, right? And write just what we have, because it's a root number. There's a root attached. So we could have 240 root 2, right? And we have sine 100, right? Pi t. Pi is a value, right? So this is how we write the, what do you call it? The voltage, right? From the voltage source, we represent it as a function of time, right? So now we go to the current. Let's see. So now we have everything. Do we have everything? So let's see. The frequency, yeah, the frequency is the same. Right, the frequency is the same because it's coming from the same source. So we have the frequency. We don't need to. We have the frequency. 2 and pi are constant. This is not changing. The only thing we need is the Im, right? So now let's get to that first. So the Im will be, as we've seen, root 2 times the what? The V, sorry, not V, IRMS times the IRMS, right? Root 2. And then we know the IRMS, which we were given in the statement, it was 10, right? So that'll be 10. So basically we end up with 10 root 2 amperes. If you want, you can change it to values, right? So let's see. So that's 10 root 2, right? Or you can leave it in this way. This one is simpler. The one with the root is simpler, right? Yeah. So now that we have this, we go on and write the current, the AC current as a function of time. We have the peak, which is 10 root 2, right? What do we have next? Sine, right? So sine, right? And then what's next? 2 pi ft, right? So let's see. So 2, so it's 2 pi ft, and then f is 50. So then 2 times this 50 here gives us 100, right? So we have 100, right? So then we have pi, right? And then we have t, right? But then there's a slight something that we must add here, right? So when we go back to the phasor, right, which we've written here, the phasor for the system, is what we have to be this, right? This is, right? You can see that when we actually wrote the current in reference to the voltage, right? And then there's a phase angle. So this one makes it simpler to write the whole thing. When you look at the phasor, it even helps you to write the quantities or the sinusoidal quantities as a function of time, right? So we know that the difference or the phase shift is 30. So then, which one is leading, which one is lagging? It's clear that the voltage leads the current, or the current lags the voltage, right? And because at the moment you are trying to represent the current is the focus, right? So the current what lags, as we were saying. You could write it in two ways, either using lead or lag. So basically, when we move this way, it's leading, right? So that's a plus. But when we move, when it's somewhere here, and then you have to move from the reference to that one, meaning that particular one lags, right? So that's a minus, right? So lead, so let's write it somewhere. Where is it? Okay, so then lead is positive, and then lag is negative. We use the negative sign to represent that, right? Okay, and then we know that the current, what, it lags the voltage, right? So it lags by how many? What's the phase difference? 30. So then 30 degrees a minute. Yes, so that's it. Yeah, so 30 degrees here. So then it's clear that the current lags the voltage. So let's see. It's just the same equation, but then there's a phase difference. So we could see clearly what's actually happening. So let's see. Okay. So there's the voltage. There's the voltage. Let me write this also so it's clear. So one important thing is that when we are representing it, let the root be where it's supposed to be, else it can get confusing, right? So the root is just to the 2, right? The sign is not affected by the root, right? And then we have the current. The phase difference showing very clear. Yes, right. So you see, their peaks are different. So these are their peaks, right? And then all this side here, this is their peak. Their peak. So they are both sine waves. So sine, right, and then sine. And then we have the pi, 100 pi here, 100 pi t, 100 pi t, right? But then the voltage lags by what? A phase difference or a fixed angle of 30, right? So that's why we have minus 30 here. Yeah, so that's it. All right.